Thanks a lot, Anupam. I should thank the other organizer for the invitation. Do you see the slides?
Yes.
Okay. So the title of my lectures was slightly vague. I did not really explicitly mention what it was about. I said it was about structure of finite groups of Lie type. I had not really decided, finalized on the things that I would like to talk about, but I thought I will take a call on the topic that I would present by looking at how other topics are accepted and how they are assimilated by all students. So it seems that it would be useful to talk about conjugacy classes in various algebraic groups. I think, so far we have seen many tutorial problems where conjugacy classes do come, and even in the other theme where word maps and so on are described, even there conjugacy classes have been very useful. So studying conjugacy classes would be a good idea. That's what I feel, and that's the thing that I'm going to talk about. Mainly, I am going to talk about So mainly I'm going to follow this article by Springer and Steinberg. This is the title of this article is Conjugacy Classes. This is from the proceedings on a conference, and it's a lecture note in mathematics from 1970, and it's a very, for subjects other than mathematics, such an old thing, more than 50 years old article may not be very useful, but for mathematics, this is a very priceless article. It's more basically an expository article. It's very long, and many proofs are given. But we will not be giving or discussing proofs in this lecture and the next one, but we will try to see some examples, basically for SLN. And then we will have tutorial problems where we will also touch upon some other groups. If one wants to look at more details, then there are these two nice books by Steinberg. One is the lectures on Chevalier groups. This is from 1967-68. Recently, the American Mathematical Society has also brought it out in print. So I think it's in the university lecture notes of the AMS that is available online if you know where to search. And then there is this memoirs of the AMS. This is a research article actually, the second one by Steinberg again on endomorphisms of linear algebraic groups. So conjugacy classes is something which is very classical, more than 100 or so years even before this paper. But this paper collects all results very nicely and presents them from the point of view of conjugacy classes in algebraic groups. So as is needed, we will have to have some notations. So we start with a reductive or a semi-simple algebraic group. We will also take it to be connected, and we assume that this group is defined over some algebraically closed field. T denotes a maximal torus in this group G. So let me say what maximal torus is or what a torus is. So whenever we have this linear algebraic group, so in general an algebraic group is simply the solutions of some polynomial equations. But if we take the underlying variety to be an affine variety, then this algebraic group is also a linear algebraic group in the sense that there is some faithful finite dimensional representation for this group G, and therefore in some way whatever complicated multiplication you may have on this affine algebraic variety, you can always see it as matrix multiplication. That's the beauty of working with affine algebraic groups. So once you have matrices at your hand, then you can talk about when a matrix is semi-simple, when a matrix is unipotent, and accordingly for this faithful representation, you can define your element in the group G to be semi-simple or unipotent if the corresponding images are so. And I should also tell you that, when we are also read the last line, which says that we shall identify G with GK. So often, whenever we talk about some element in G, we will really mean that we are taking an element in GK. All right, so this is about semi-simple and unipotent elements. Now, a torus in a linear algebraic group G is a connected subgroup consisting only of semi-simple elements. And the maximal one among them, which exists because of the dimension reasons, the group G has finite dimensions, so you cannot have. We also take torus to be connected. So a connected group which consists only of semi-simple elements is a torus, and the maximal one in the group G is called a maximal torus. Okay, so once you fix such a maximal torus, then we denote by capital X the character group of this torus T. So character group means that you are looking at all algebraic group homomorphisms from the torus T to one-dimensional abelian semi-simple group, which is the GM. Okay, so one-dimensional group consisting of only semi-simple elements, that is GM. So algebraic group homomorphisms from T to GM, those form characters. They form a group naturally because you can take product inside G. If you have two characters, the product of them is simply chi1, chi2 acting on some small t is chi1 t, chi2 t. So that gives you a group structure on the set of characters. We call that group to be capital X. And if you have studied some bits of linear Lie algebras, then you know the next thing, the set of roots of capital G with respect to T. So your capital T will act on the Lie algebra. T consists of semi-simple elements. The whole group G acts by adjoint representation on the corresponding Lie algebra. So you can restrict it to your maximal torus T. Since it consists only of semi-simple elements, all representations of this maximal torus are sums of one-dimensional representations, and the characters which appear there for the in the decomposition of the Lie algebra for the representation of the torus T, along with the zeros, the non-zero characters that appear, they are called roots of G. And so you have some certain spaces inside the Lie algebra which are on which your torus acts by these characters. That means you will have that the adjoint action of small t on some Lie algebra element is simply chi t, where chi t is now some scalar into the same Lie algebra element. So these are one-dimensional spaces which are invariant with respect to the torus, and therefore the action by the torus is given by some scalars, and those scalars correspond to the corresponding characters. So roots are precisely the non-zero characters which appear in the decomposition of the Lie algebra under the adjoint action of the torus T. Now, since our group is connected, whenever you have such a root subspace, there is also a root subgroup inside the group G itself. And there the torus T will act by conjugation. So this U alpha, this is precisely the set of elements in your group G on which capital T acts by conjugation, and the conjugation is given inside. So these happen to be unipotent elements, and we will see some examples soon, so that will make it clear to you. But these are one parameter subgroups, so they are isomorphic with the base field. And once you fix an isomorphism, then the conjugation action of the maximal torus is simply the multiplication by that corresponding character inside that one parameter subgroup. So that is what we have here, that the U alpha, for each root alpha, there is this root subgroup. And then we look at also W, which is the normalizer of the torus upon torus. This is called the while group of G. And once you have these all U alpha, there will be only finitely many roots because your capital G is finite dimensional. Therefore, the Lie algebra that you have has finite dimension as a vector space over K. And your U alpha are the roots, so they will correspond to invariant subspaces inside the Lie algebra under the torus action. There can only be finitely many. It also happens that for each root there is only one-dimensional space. So there are the dimension of the corresponding root subspace is only one. And so these U alphas are also therefore the precisely unique one parameter subgroups. Then if you can take the product of all these U alphas, so these U alphas are root subgroups, you can take product of all these U alphas, that will still give you a subgroup, and that is called the unipotent subgroup. And then corresponding B, which is T into U, this is called a Borel subgroup. This is a Borel subgroup. Let me not say that this is called a Borel subgroup, but this happens to be a Borel subgroup. So these are some notations. Unfortunately, one cannot do without specifying some notations. So many of these things would have been seen by you already, and we will also soon see an example.
And
So
sir,
before we go to examples, there are these very important results. So I
sir,
have talked about U being product of U alphas. Was there a comment by somebody?
yes, sir. Sir, here action of W on T is also a conjugation, na?
Action on W on T is given by the action of the normalizer. Yes. So the action is only given by conjugation.
Conjugation.
Yes.
Okay. Yes. Yes. Okay.
Okay. So here we have written U as product U alpha. And then we have also written Borel as T into U. So this, when we are talking about product U alpha and we are working inside matrices which do not commute with each other necessarily. So you may ask whether order is important, whether it is important what alphas you keep first and then some other alphas and so on. And this is a very important result which will go into the background of all the further results that we discuss, which is that the order doesn't matter. So product U alpha to U, the order doesn't matter. Whenever you fix an order for once and all, you fix an order, and once you have fixed this order, then this product map gives you an isomorphism of varieties. And
So
similarly,
excuse and
yes,
yeah,
Shiv.
yeah, this product over U alpha, you will have to take only positive root, right?
I should
Not
take
alpha.
only positive, correct. Yes,
Yeah, that's all.
true. Yeah, thank you, Shiv. So once you fix the positive roots, then the order doesn't matter. You will take the product over all these U alphas in a fixed order. And once you have this fixed order, then the map towards capital U gives you an isomorphism of varieties. So what does it mean? It means that I can decide if I want to write an element in capital U. Maybe I should first do some examples and then come back to this. So my next slide is about examples in SLN, and then I come back to this. So for SLN, the torus is the subgroup of diagonal matrices. This is a torus. This is a maximal torus. And we have that this torus is isomorphic to n-1 copies of GM. GM stands for the multiplicative group, which is the one-dimensional group consisting only of the semi-simple elements, or GM can be thought of as GL1. Okay, so our maximal torus in SLN could be taken to be the subgroup of diagonal matrices in SLN. What are the characters for this torus? So there are all possible characters. In particular, you can look at these characters. Whenever I is not equal to j, we have these characters chi corresponding to that particular pair ij, which sends your diagonal matrix T1, T2, Tn to Ti, Tj inverse. These are some characters, and these are precisely the characters which will occur in the root decomposition, the root space decomposition. So U chi is the group of matrices that agree with the identity matrix outside the ijth position. So your ijth position, you are taking I not equal to j. So for instance, you may simply take 1, 2, the first row, second column, and that will correspond to the torus which is sending T1, T2, Tn to T1 upon T2 or T1, T2 inverse, right? And the corresponding one-dimensional subgroup of the group of matrices of determinant 1 is precisely that set of elements which agree with the identity element outside that 1, 2 slot. So identity element has all the diagonal entries 1 and 0 everywhere else. So these matrices will also have 1s on the diagonal, 0s everywhere else except possibly at the 1j position, 1-tooth position. So if you have 0 there, it will give you the same identity matrix which has to be there in every subgroup, of course, but you may also have any non-zero entry there. So these U chi are naturally isomorphic with the base field, or similar to the GM that we have above, there is also the GA, and these U chi are all isomorphic with GA. So this is the U chi which corresponds to the root I comma j, where I is not equal to j, and the positive ones in this. So what if you look at the set of roots, then there is some natural order on them, and here you may take whenever I is less than j, all those form one particular subset which is invariant under this order, and these are the ones that Shiv was talking about to be the positive ones. So these are the ones which we will collect. So if you have I less than j, then these are the corresponding U chi which correspond to the upper triangular matrices. So the upper triangular matrices, you are taking them for all possible slots I less than j, and therefore you are going to get all possible slots which are there above the diagonal. And that gives you the full upper triangular matrices consisting of unipotent elements. So all the upper triangular matrices consisting of unipotent elements, those the U that I have written below, that is the group generated by the U alphas where I is less than j. And if you also throw in the torus T with that, then you get all possible upper triangular matrices, not necessarily unipotent. So that gives you a Borel. I think now this is quite clear to everybody that the upper triangular matrices form a Borel subgroup by looking at previous tutorials and so on. So these are the corresponding Borel and the corresponding U in SLN. And moreover, the normalizer of the diagonal matrices, that is precisely the set of monomial matrices. Monomial matrices are the ones which have exactly one non-zero entry in each row and in each column. And once you go modulo the torus, then we have the permutation matrices, which can be identified with the symmetric group Sn. So let me go back to the previous slide and the one before that. So I believe that for the group SLN, we have seen all possible these things. So T, I told you, is the set of all diagonal matrices. The character group is the set of all characters for this torus. So whenever you have a R dimensional torus, the character group will be a free abelian group of rank R. So for us, it will be a free abelian group of rank n-1 if you are looking at SLN. Then I also told you what the set of roots are. I also explained the root subgroup for each root I not equal to j. While group has been told, and this product is to be taken only over positive roots. And this statement now is very important because we may decide that when we are looking at some element in capital U, so you have some element in the upper triangular matrices, and you want to write it as a product of elements coming from each of these slots. Once you fix some order, then this isomorphism will tell you that there is exactly one way to write them. Okay, so once you fix this isomorphism, then we will have that there is exactly one way to write an element of capital U as a product of these root subgroups. And this is something which is very useful. This uniqueness happens to be very useful. For instance, when you look at the corresponding case over finite fields and you want to count elements, then this uniqueness is very useful. Okay, similarly, this map is an isomorphism. So these are natural maps. Natural maps in the sense that they are given by simply the multiplication map. You have that U alphas are subgroups of the group G, and you can take tuples of elements coming from each positive U alpha, and then you take their product that lands inside U, and that map is an isomorphism of variety. Similarly, once you take a torus element and some element in capital U, take the product, you land inside capital B. That is also an isomorphism of variety. Moreover, this is a statement which is also useful, which is that U is a maximal connected unipotent subgroup of G. A unipotent subgroup of G is a subgroup which consists only of unipotent elements. Just like a torus was something which consisted only of semisimple elements, here is the counterpart for unipotent elements. So this is a unipotent subgroup. It is connected and it is maximal with respect to these two properties. And your B is maximal with respect to being connected and solvable. You know, meaning working with the matrices, it will be clear to you that if you have T into U, then the torus is, you know, we know that all the U alphas are preserved under the torus by the conjugation action. So capital U is preserved under the torus by conjugation action. And therefore, the U is a normal subgroup inside capital B. And once you go modulo that, the isomorphism of varieties will tell you that the quotient has to be isomorphic to the torus. So the quotient is an abelian subgroup and you are going modulo a unipotent subgroup, and unipotent subgroups are easily seen to be nilpotent subgroups. So you have some central series which go to identity. Okay, so you have a solvable normal subgroup, modulo which you again get a solvable subgroup. Therefore, your Borel is a solvable group. It is connected because both T and U are connected. And then it happens to be a maximal connected solvable subgroup of G. Okay, and there is this last statement on the same slide, which is written very, very innocuously, but it's a very important statement. It's called Bruha Decomposition for the group G. So if you choose some representatives for your while group element, remember the while group is nothing but NT modulo T. It's the normalizer modulo the torus. So you choose for each W in W, you choose some representatives in the normalizer. Then this set gives you a representatives for N by T. These are coset representatives for the torus, the cosets of torus inside the normalizer, but these are also system of representatives for these double cosets B, G, B. The Borel acts, the B cross B, if you take B to be your Borel, then B cross B acts on G, where one Borel element acts on the left hand side and the other on the right hand side. So if you have B1 comma B2, its action on some small g is B1 G B2 inverse. It's on the other side, so you will have to put an inverse there. Okay, so once you have this action, then the orbits under the action of B cross B inside capital G are the double cosets. These are finitely many, and these finitely many double cosets are also given by the corresponding representatives are also given by these representatives of the while group inside the normalizer. So NW happen to be not just the representatives for the torus in the normalizer, but they are also representatives for the double coset of the Borel inside the group G. So for instance, if you were to look at SLN, although I have not done this exercise, maybe I should have perhaps explained it here, but it can perhaps be taken inside in a tutorial, that if you take your standard permutation matrices as the system of representatives for the while group inside the normalizer of the torus, then every matrix by left or right multiplication of the upper triangular matrices can be reduced to such a matrix. So how does one do this? So for instance, if you look at the first column, you have a matrix. Let's say we are working with GLN instead of SLN, although there is very small difference. So if you work with GLN, then you know that the first element cannot be the zero, the first column cannot be the zero column. So when you start from the end of that first column, you will hit some non-zero entry at some point. And then by multiplication by a suitable diagonal matrix, you can make that entry to be 1. And once you have made that first entry to be 1, then all the above entries by some linear combination of this particular row, all the above entries can be made 0. So you have some left or right multiplication of upper triangular matrices, which will give you that each column, you will start by the looking at the first column. So in the first column, you will have achieved only one non-zero entry, and that is equal to 1. Once you get that entry, then you can use it and make the whole part of that particular row to be 0. And then you will continue with the second column. And this way, if you go, you would have achieved the, perhaps it's called Gaussian decomposition or Gaussian standard form, that every matrix is equivalent under the action of the upper triangular matrices on the left and right to a permutation matrix. This is precisely the Bruha decomposition in general reductive groups. Okay, so this is what we have, that the choice of representatives that you take is also a system of representatives for your double coset action of the Borel subgroup on the group G. Okay, this is a bijection. Okay, so up to here we were discussing only groups which are defined over K bar. But we would like to come back to our finite groups of Lie type. You know, the title of my talk says with examples from finite groups of Lie type. So here is a recipe to construct finite groups of Lie type. So they are obtained in the following way. In general, if you have a reductive group G over an algebraically closed field, and if you take an endomorphism sigma of this group G, endomorphism meaning it's a homomorphism from G to G. It may not be an isomorphism, but just a homomorphism. A standard example is given in the next line of the Frobenius endomorphism. So if you take your group to be defined over a field of positive characteristic, an algebraically closed field of positive characteristic, and then for every power of the characteristic, you have the corresponding Frobenius endomorphism. What is the Frobenius endomorphism? Think about the faithful representation that I have told you earlier. So with respect to the faithful representation, this Frobenius endomorphism is simply raising each matrix entry to the qth power. Because your Q is a power of your characteristic, this happens to be an endomorphism. This is a homomorphism of the group. And if you are looking for matrices which are fixed under this homomorphism, that would mean that each matrix entry has the property that it is its own qth power. So each matrix entry belongs to a finite field FQ, and therefore the set of all such elements is finite. So when you are working over a positive characteristic field and you are taking the Frobenius endomorphism, then the set of fixed points is a finite group. Okay, so that's what has been explained in the next line. So for any endomorphism, we will define G sigma to be the subgroup of elements which are fixed by sigma. And if your sigma is the Frobenius endomorphism, then these are finite groups. And these are what are called the finite Chevalier groups. So for instance, if you wanted to get SLN FQ, you have to consider SLN FP bar, the algebraic group defined over algebraic closure of this FP, and then take the corresponding Frobenius endomorphism for Q and take its fixed points. That is your SLNFQ. There are also some other Chevalier groups which are given by obtaining some, we will twist the Frobenius endomorphism with some more endomorphisms. And this is the work of Steinberg and Chevalier, which will give rise to these groups. So for instance, if you were interested in getting the unitary groups or maybe the SUNs, then you have to not just take the Frobenius endomorphism, but also compose it with the inverse transpose. So those are the maps that you should be looking at. Those are the endomorphisms that you should look at. And then the corresponding fixed points give you the finite Chevalier groups. And as it happens, the conjugacy classes of these finite Chevalier groups correspond very nicely with the conjugacy class, some certain conjugacy classes in your algebraic group. So this whole article of Springer and Steinberg is about this relation. And that's what we are going to do. Moreover, these notions of T, sigma, U and B, they carry over to G sigma with some suitable modifications. So you have a torus if you are looking at your group G and you are looking at G sigma by looking at some nice Frobenius endomorphism, or let me say Frobenius like endomorphism, then there is a torus T which is fixed by this Frobenius endomorphism. So you will have this T sigma is sitting inside G sigma. You can talk about characters of that T sigma. So that will give you sigma sub sigma, the capital sigma sub small sigma. Those will be the characters of the torus that you have below. And then there are also the capital U sub sigma and capital B sub sigma for some suitable U and suitable B. So all these notions do exist for the corresponding finite groups with small modifications. And for instance, for groups like SLN, no modifications are needed. So when you take the diagonal matrices are invariant under the Frobenius endomorphism, right? If you apply the Frobenius endomorphism is applied to entry of the matrices. Therefore, once your matrix is diagonal, all the other entries are 0, and the 0 will be sent to 0 by Frobenius endomorphism. Therefore, a diagonal matrix is sent to a diagonal matrix, right? So you have this torus of diagonal matrices inside SLN, which is preserved under the Frobenius endomorphism sigma. Therefore, if you take the fixed points inside this torus, that will correspond to some torus inside your corresponding SLN FQ. And indeed, you will see that your FQ cross times FQ cross times FQ cross, that does give you a maximal torus inside SLN FQ. So those are the things which I mean when I say that the notions carry to G sigma with some small suitable modifications. Okay, so once we have these, then we can now think about conjugacy classes in G sigma. So our aim is to understand conjugacy classes in these finite groups G sigma. And one would want to see, so if you take an element in this finite Chevalier group G sigma and you take its conjugacy class above. So for instance, if you take a matrix inside SLN FQ, imagine that matrix sitting sitting in SLN FQ bar, and you can ask what are the conjugacy classes there, because once you go to an algebraic closure, then you have the notions of algebraic geometry that will help you studying all these notions. So you can ask how does the conjugacy class of this matrix look like when you go to algebraic closure. And once you are there, then you can ask that now I have this huge big conjugacy class. If I intersect it with my G sigma, how does it look like? Do I get a single conjugacy class, or does it split as a union of several conjugacy classes? So those are some small questions that one can ask. So there are these things go in two ways. So first of all, if you have a conjugacy class above, which is fixed under the sigma action, then it should contain an element which is fixed by sigma. These are some very non-trivial statements, and these are proved in Springer's, Steinberg's endomorphisms of linear algebraic groups. So we will not spend time in proving these, but these are some very non-trivial statements. You have a subset which is invariant under sigma, and we want to say that it contains an element which is preserved under the sigma. But that does hold if your subset is the set of conjugacy, it is a single conjugacy class. Okay, so you have a reductive group defined over FQ bar, and you have a conjugacy class above over FQ bar, which is invariant under sigma. As a set, it is preserved under sigma. Then it should contain an element which is fixed by sigma. So in particular, there is a matrix in that conjugacy class which has all its entries as elements inside your FQ. Okay. Moreover, clearly, if you take some matrix which is fixed by sigma and take its conjugacy class above, that will naturally be invariant under sigma. So these two notions are surprisingly one and the same. Moreover, suppose you have this conjugacy class C above, and you have the element X which is preserved under the sigma action, then the classes of the finite group G sigma which are obtained by intersecting the class above with G sigma. Those are in one-to-one correspondence with this Galois cohomology set. So in this case, actually it can be explained very easily. So let me spend some time on this. H1 sigma A is a notation to denote some certain class. So what is that set that we are going to denote by this H1 sigma A? This is precisely the capital A that you have in, so wherever we will talk about H1 in this two lectures, we will have the A to be a group. For instance, here we are looking at Gx mod Gx naught, the centralizer modulo the connected component containing the trivial element, the identity element. So it is a group, and there is an action of sigma. It's a subgroup of G ultimately. So therefore, there is an action of sigma on this set capital A, and we say that two elements in A, capital A, are equivalent under the twiddle if there is some element C with the property that A is CB sigma C inverse. So this is called twisted conjugacy. You have an endomorphism of capital A, and we say that A and B are twisted conjugates of each other if for some C in A equal to CB sigma C inverse. And the twisted conjugacy is important because it gives some very nice one-to-one correspondences with the sets that we are interested in. So for instance, when you take this conjugacy class above, which is capital C, and you are intersecting it with our G sigma, then what you need to do is to find the centralizer of the element X and see what are the connected components in the centralizers. So luckily, whenever we are talking about algebraic groups, algebraic group is connected if and only if it is irreducible. So there are many ways to see when some algebraic group is connected. So for instance, if you know that your algebraic group is constructed by using a few copies of GM and a few copies of GA, then you know that your algebraic group is connected. For instance, your capital B, which we had constructed some slides back, using the torus and the unipotent subgroup capital U. The U was obtained by U alphas, which are all one-dimensional abelian groups GA, and the torus is constructed by using GMs. All these congruent, the constituents, the ingredients that are used in constructing this capital B, they are all connected one-dimensional subgroups. And we had isomorphism of varieties. In fact, for connectedness, you don't need isomorphism of varieties. A surjection would be enough. So whenever you have a group which is constructed by means of connected groups, then your group will be connected. Or you may look at the corresponding coordinate ring. If that's an integral domain, then you know that your group has to be connected, because connectedness and irreducibility happen to be the same concepts for algebraic groups. Moreover, just by looking at the group structure, an algebraic group G is connected if it has no finite index subgroup. So there are these various nice small statements that one can use, but typically when you have some special elements X, then you would know how the centralizer looks like, and often simply by looking at the centralizer, you will be able to determine whether or not it is connected. So you take this centralizer, go modulo that particular connected component which contains the identity element. That happens to be a normal subgroup of this subgroup. So you get a finite quotient. Basically, you get a set of connected components of your centralizer, and then there is a natural action of this endomorphism sigma on that. So for instance, later we will also be talking about NT upon T instead of ZX upon ZX naught, where we will have the while group. We will talk about sigma action on while group. If you have a subgroup of capital G, we know how sigma acts on that. And if you have a subgroup of capital G modulo another normal subgroup which is invariant under the sigma action, then the sigma action will carry to the quotient. And that's what we have here. The sigma action on ZX mod ZX naught is defined by simply defining it on ZX. because the connected component is invariant under this Frobenius endomorphism. So you simply compute the H1, and the number of these H1s is precisely the number of conjugacy classes which correspond to the intersection of C with G sigma. So for instance, we will see it in the tutorials that for GLN, all the centralizers are connected. Whenever you take your G to be GLN and you take any matrix, take the centralizer, all these centralizers are connected. Therefore, the highlighted quotient that I have here, those are all trivial groups. And therefore, you have no element here except the trivial element, which means that when you have some elements in G sigma, they are conjugate if and only if they are conjugate above. If you have studied your basic algebra from books like Herstein, then Herstein has this exercise to show that whenever you are looking at some field K, then two matrices in MnK are conjugate if and only if they are conjugate in MnK bar. And this is a very fantastic way to prove that simple-minded exercise. But this is a very useful comment, and already, meaning what if people know about what are the forms of various objects which are defined over some general fields, then this means that whenever your centralizer is connected, then there are no non-trivial forms of the conjugacy classes of that particular element X. Okay, so when you have Gx is connected, then the conjugacy class above does not split when you intersect it with G sigma, which means again that two elements of C intersection G sigma which are conjugate in G, they will also be conjugate in G sigma. The other way is quite easy to see. Whenever you have two elements which are conjugate in G sigma, then you have the conjugating element in G sigma, and then you have the conjugating element above also. But the reverse implication also holds simply by looking at the connectedness of this Gx. So these are some examples. Whenever we take G equal to GLN, then all centralizers are connected. As we will see in some tutorial problems, that centralizers of matrices in GLN, they are all connected. Therefore, there is no splitting. And you may take the same statement holds actually when we are looking at UN instead of GLN. Instead of looking at the endomorphism to be the Frobenius endomorphism, you take its composition with the inverse transpose map, and the previous comments still hold. They hold for any endomorphism of your capital G, and therefore the same statement holds that two elements in UN are conjugate if and only if they are conjugate above. Okay, and for SLN, there are some elements whose centralizers are not connected. Again, in the tutorials, we have seen some. So here instead of n, it should have been 2. So already for n equal to 2, we have examples. So suppose you have the set of unipotent elements in SL2. Okay, and in particular, if you take the element 1, C0, 1. So you are taking unipotent element, therefore there is 1s on the diagonal. You also assume that there is 0 below the diagonal. You are not taking some conjugate of the unipotent element, and you put some non-zero entry above. And within SL2, if you compute the centralizer of these matrices, these will correspond to the precisely the upper triangular unipotent subgroup direct product plus minus identity. The scalars inside SL2 give you a finite subgroup of order 2 plus minus identity. You are assuming that the characteristic is not 2. Okay, so we have plus minus identity as the scalars, and upper triangular unipotent matrices of course form an abelian subgroup. So when you are computing the centralizer, for instance, of 1101, that centralizer is plus minus 1 on the diagonals, meaning you will have either 1 1 on the diagonal or you will have -1 -1. and you can have any entry above. So this is a subgroup which is isomorphic to the upper triangular unipotent subgroup, which is GA times plus minus identity. So it has a factor of order 2, therefore this is not a connected subgroup. And this factor of order 2, that will come into picture and give you that when you take the conjugacy class above and you take intersection with SL to FQ, you do get two conjugacy classes, as we have again seen. So 1, 1, 0, 1 and 1 epsilon 0, 1, where epsilon could be, for instance, the generator of the corresponding cyclic subgroup FQ cross, or you may take any element inside FQ cross which is not a square in FQ cross. So these are the two conjugacy classes of unipotent matrices in SL2. Whereas in GL2, you are going to get a single conjugacy class because the centralizers in GL2 are all connected. It's more or less half the time. So if there are any questions, I will be happy to try and answer. Of course, there are many other people also in the audience and people can make comments. Roughly, I think I have also reached the half stage of my notes, my slides. Okay, so I will go ahead if there are no further questions. This is once again a general result in the sense that we will not have any condition on the characteristic of the base field. This is the Jordan decomposition inside your group G. The statement is as follows. You start with some element in G, then there are elements S and U in G with S semisimple, U unipotent, and they satisfy this equation. So there are two equality signs. The first equality sign means that your group G, your element G is the product of these two elements. So you have G to be product of a semisimple element and a unipotent element. And the second equality tells you that S and U commute with each other. And therefore, they will also commute with the whole G, with the element G. Okay, and if you fix these properties that you are writing your G as product of semisimple and unipotent elements which commute with each other, then these S and U are unique with these properties. In fact, you have even more. You actually have that when you take any faithful representation of capital G, then in that representation, you in the corresponding set of matrices, you can actually see S and U as polynomials in G. So quite a lot can be said about the semisimple parts and the unipotent parts of your small g. What is important for us is that these semisimple parts and unipotent parts are uniquely determined by the group element G. And this decomposition is very useful. One instance where it is useful precisely because you can see the semisimple part and unipotent part as polynomials. Therefore, you have that if you have some endomorphisms of your algebraic group G, then the decomposition is preserved. It is preserved under all homomorphisms. So, if you are taking any homomorphism from some algebraic group G to another algebraic group H, and you have image of your small g which goes to say small h, then image of the semisimple part of G is the semisimple part of H. Image of the unipotent part of G is the unipotent part of H. So that is what we mean by saying that this decomposition is preserved under the homomorphism. So in particular, under the endomorphisms like Frobenius endomorphism or twists of those, we have that the corresponding decomposition does hold. And therefore, whenever you have G which is fixed by sigma, the corresponding S and U are also fixed by sigma, right? Because if you were to apply sigma to G and then you will have sigma S, sigma U, the product of sigma S, sigma U gives you sigma G. If sigma g is equal to g, then it gives you that sigma s, sigma u is g. Further, sigma s is semi-simple because s is semi-simple. Sigma u is unipotent because u is unipotent. And su commute. Therefore, sigma s and sigma u will also commute. So if your sigma s is not s and sigma u is not u, then you are going to get another decomposition for G, which should not be true because the decomposition of G into the semi-simple and unipotent commuting elements is unique. Therefore, whenever G is fixed by sigma, the corresponding S is fixed by sigma, corresponding U is fixed by sigma. So whenever your small g is an element defined over FQ, these S and U will have to come quietly. They will have to follow your small g and they will have to sit in the subgroup defined over in the group defined over the finite field FQ. So if you have a matrix, for instance, which has all entries coming from FQ, the semi-simple parts of that matrix will also have entries coming from FQ and unipotent parts will also have entries coming from FQ. Okay. If you are looking at finite groups of Lie type in particular, then these unipotent elements are nothing but the elements which are P elements. Their orders are powers of P. And semi-simple elements are also characterized by this property that they are P prime elements. That means that their orders are co-prime to P. So here we have a finite group G sigma, and within them an element is semi-simple if and only if its order is co-prime to P, and some element is unipotent if and only if its order is a power of P. So the Jordan decomposition helps a lot in studying various these things, and here is a basic application of Jordan decomposition. That of course, if you are taking anything which commutes with G, then these elements will have to commute with S and also with U. Right? If you are taking some H which commutes with G, that means H inverse is G. You may look at the homomorphism which is given by the inner automorphism with respect to small h. And we have already seen that the homomorphisms will preserve the Jordan decomposition. So therefore, whenever some element commutes with G, it will have to commute with S and it will also have to commute with U. Moreover, by the property of G being SU, you know that whenever something commutes with SU, it will commute with G. So the centralizer of your G is the intersection of these two centralizers. So you have the semi-simple part, its centralizer, intersect that with the centralizer of the unipotent part. Take these centralizers in the full group G. And this is also equal to the centralizer of the unipotent part inside the centralizer of the semi-simple part. We will see that centralizers of the semi-simple parts are reasonably well understood. These will happen to have some groups with nice properties. So you can actually understand those groups nicely. And this Jordan decomposition then tells you that centralizers for general elements, they are basically centralizers of unipotent elements inside some well understood subgroups. So this is very important application. We have realized that centralizers are very useful because we can compute how many classes your algebraically closed conjugacy class splits into when you intersect it with G sigma. So centralizers are very important, and the centralizers can be understood by looking at essentially the centralizers of semi-simple elements and the centralizers of unipotent elements. So you have to basically concentrate on these two classes, the semi-simple classes and unipotent classes. All right, I believe we all agree with this. Now, if you were to look at GLN, for instance, and you are looking at semi-simple elements, then we know that they all, by definition, semi-simple elements are diagonalizable over algebraic closure. So they are given by some diagonal matrices, and you have some entries in the matrix, the diagonal entries, which are simply the eigenvalues of your matrix. And whenever two matrices are conjugate, their corresponding eigenvalues will have to be the same. So for semi-simple matrices, there are infinitely many conjugacy classes because you have infinitely many possibly distinct subsets of eigenvalues. You have n tuples of eigenvalues, which are infinitely many. So the conjugacy classes of semi-simple elements are infinitely many. But inside GLN, the conjugacy classes of unipotent elements are only finitely many. That corresponds to the Jordan form, the normal form. So you have ones on the diagonal, and you have some entries above the diagonal where you have ones, and then you have zero everywhere else. Every unipotent matrix is conjugate to one such matrix. And moreover, among them also you have some nice conjugacy relation. For instance, if you have, you can write any unipotent matrix as product of block diagonal matrices, where each block consists of ones on the diagonal, ones on the super diagonal, and zero everywhere else. So each unipotent element is conjugate to one such matrix, and moreover, the decomposition gives you a partition of n, and whenever you get the same partition, the corresponding matrices are conjugate. If the matrices are conjugate, you are going to get the same partition. But if the partition is the same, then again you have the same conjugacy class of the unipotent matrices. So in GLN, the number of unipotent conjugacy classes is basically the number of partitions of n. Okay, so for instance, in GLN, in GL2, you have only one non-trivial conjugacy class of unipotent elements, which is given by 1, 1, 0, 1. In GL3, you will have the 1, 1, 0, 1 and small 1 by 1 block below, or you will have the identity block which is there, or you will have the regular unipotent, which is ones on the diagonal and the two ones above the diagonal. These are the three conjugacy classes which correspond to the partition of 3 as 3 equal to 3, or 3 equal to 2 plus 1, or 3 equal to 1 plus 1 plus 1. So the unipotent elements inside GLN, they give you only finitely many conjugacy classes. And one wondered whether this is true in general for reductive groups. And this is a very old theorem, although I have given Richardson's name here. I think this is, so let me share this another tab here for you. There is a theorem of Richardson which proves it in a very good set of characteristics, and then that was generalized by Lustig. Richardson's theorem is from 1967, and Lustig's result is from 1976, less than 10 years after that. And let's read the review of this, which is again given by Steinberg. So he proves that it was a conjecture. For instance, you may look at Steinberg's paper in the ICM 1966, that the number of unipotent conjugacy classes in a connected reductive group G defined over an algebraically closed field K is finite. So the work of Dinkin and Constant showed that this is true whenever characteristic is 0. So whenever characteristic is 0, there is this work of Dinkin and Constant, which says that for characteristic 0 fields, this is true. And then it was Richardson in 1967 who proved that this is true in the case of characteristic being good. So when you have a reductive group, your reductive group is a product of a central torus and some finitely many simple groups. And there is a notion of a prime being good or bad for each simple groups, and actually it can be written down. So for instance, if your simple groups are of the type AN, then every prime is good. If it is of the type BN, CN and DN, then 2 is a bad prime for these groups. If it is G2 and F4, I think 2 and 3 are bad primes, and if I am not incorrect, then there are no other bad primes. Or maybe for exceptional groups E6, E7, E8, I will have to be careful. There are some possibly bad primes. So except finitely many primes for each group, we have that the result is true by Richardson's theorem. And then Lustig completed this in 1976. He proved that this result does indeed hold. So if I can go to my slides now, this is Richardson's theorem, that whenever you have a reductive group over an algebraically closed field of characteristic which is good for the group G, then the number of unipotent conjugacy classes in G is finite. And Lustig simply proved that this theorem holds in all characteristics. So this is a wonderful result and a very, very useful result. The proof has flavor of algebraic geometry. Proof is very interesting. You may want to look at it. Springer-Steinberg also gives some idea of this proof. They do consider it to be a very important result. And you may also look at Richardson's own paper, which is also a nice paper. Okay, so this is something that we have for unipotent classes over algebraic closure. Now let's come back to our semi-simple elements in the group G. So first of all, every semi-simple element is contained in a maximal torus in G. Okay, and further, if you are looking at the group G to be a reductive group, and when you are not specifying any sigma or something, it means you are taking the points over algebraic closure. There, all maximal tori are conjugate. Okay, but if you are taking G sigma, then the conjugacy of maximal tori may not hold. In fact, it does not hold. However, the earlier result still holds, that every semi-simple element in G sigma, so you are looking at a semi-simple element in G which is fixed by sigma, the Frobenius endomorphism or its twist. Every such element is contained in a maximal torus which is also fixed by sigma. So this result holds. Okay, and this is what I meant when I said in the initial slides that the notions T, sigma and so on carry over to G sigma with small suitable modifications. So this particular statement holds without any modification, that if you have a semi-simple element in G sigma, it is contained in a maximal torus which is also preserved by sigma. So, you know, in another way, meaning a very trivial example of this would be that if you have a diagonal matrix in SLN FQ, it is contained in the set of diagonal matrices in SLN FQ. That's how trivial the statement becomes. But in general, this theorem is true. And of course, the conjugacy of maximal tori does not hold. And there are these two examples that you can consider FQ cross ... times FQ cross. So you have these non-zero elements in FQ on the diagonals. That's a torus inside GLN FQ, because when you go to algebraic closure, it gives you the maximal torus consisting of diagonal elements, and the fixed points of that is precisely the set you started with. Another torus is this FQ power n cross. So this is the set of all invertible elements in FQ power n. If you tensor this extension, you imagine FQ power n as an algebra over FQ, and now tensor it with FQ bar over FQ, then it will split as FQ bar cross FQ bar cross FQ bar n times. So the invertible elements in this algebra over FQ bar is also the set of invertible elements in each of those FQ bars. And so you are again going to get FQ bar cross times FQ bar cross times FQ bar cross n times. So as you go above, you are going to get the conjugation with respect to conjugation to the diagonal torus over algebraic closure. But this conjugation does not hold over FQ. For instance, because we all know that the FQ power n cross is a cyclic group, and when you are taking FQ cross times FQ cross times FQ cross a few number of times, you don't have a cyclic group. So these two are not conjugate below. But when you put in more points, you throw in more points, then it is likely that they become conjugate. In fact, they become conjugate over the field FQ power n already. But then they also remain conjugate above that. So there can be many more maximal tori. Up to conjugacy by G, inside G, there is only one maximal torus. But it is slightly more interesting because there is a lot of arithmetic when you are coming to these fields which are not algebraically closed. And it is indeed fitting that there are many more maximal tori, and one can actually write down the exact number of maximal tori, and that is again given by the H1 that we already have seen once. So whenever you have this sigma, the Frobenius endomorphism or Frobenius like endomorphism, then there is a maximal torus in G which is fixed by sigma. So there is always such a maximal torus. If you denote it by capital T and take the corresponding while group W, then all maximal tori in G sigma, or in other words, the maximal tori above, which are sigma invariants, and you are looking at their conjugacy classes up to elements in G sigma. That number is the same as the number of elements in H1 sigma W. So let's understand this statement again. We have understood that over algebraic closure, there is only one maximal torus up to conjugation. Any two maximal tori in a group G are conjugate. Actually, this holds more generally. This holds in any algebraic group, not just inside a reductive group. But now we are looking at reductive groups, and we are looking at some suitable endomorphism, sigma, such that the G sigma is a finite group. More generally, these are the things we are looking at. And we call these endomorphisms to be Frobenius-like endomorphisms. So the maximal tori, you collect all maximal tori in your capital G, which are fixed by sigma, which are invariant as a set by sigma. The collection of such tori is non-empty by your first statement, that there is such a torus which is fixed by sigma. So you fix this torus and you take the corresponding while group. Then you compute this set H1 sigma W. While group is a finite group, and you have H1 sigma W. So you are ultimately going to get a finite set. This set corresponds in a natural way to the sigma invariant tori in capital G and their conjugacy classes, not by the whole capital G, but elements in G sigma, which are fixed by your endomorphism sigma. So for instance, if you were looking at SLN FQ, then inside SLN, the tori which are fixed by the Frobenius endomorphism, you collect them, you take the conjugate, you would say that two of them are equivalent if they are conjugate by some matrix sitting in SLN FQ. Then the number of conjugacy classes of those tori over FQ bar is equivalent to, is the same as the number of elements in H1 sigma W. And remember that the sigma action on W is given by sigma action on the normalizer, because the torus is some subset which is invariant under sigma. So the action on the quotient is seen by the action on the normalizer. Moreover, for groups like SLN, what happens is that all these characters that I told you, the corresponding to I, j, they are all defined below. And therefore, your while group is actually defined by elements which are all having entries over FQ. Indeed, your permutation matrices have entries 1 and 0, right? So you have that for SLN, the while group is defined over the base field, however small the base field you take. The while group is defined over that, and therefore the sigma action on the while group is trivial. So when you have the equivalence A equal to C B sigma C inverse, the sigma action is trivial, so it is simply A equal to C B C inverse. And this is the set of conjugacy classes in the while group. So whenever you have that sigma acts trivially on the while group, as it does, for instance, when your while group is the while group of SLN, or whenever you have a split maximal torus, some torus which is already split, all its characters, all the roots are defined below, then you have that sigma acts trivially on the while group. And then these conjugacy classes, the classes of sigma invariant maximal tori in G, under conjugation by G sigma, this is same thing as the conjugacy classes in the while group. For instance, for GL2, the while group is of order 2. there are two conjugacy classes and there are precisely two maximal tori up to conjugacy. You have FQ square cross and you have FQ cross square. So these are the two maximal tori up to conjugacy which are invariant under sigma up to conjugation by the group GL2FQ. Okay, so these are some, although these statements can be very daunting, actual computations are very easy. You might want to check this. We have studied the tori, actually when we studied the conjugacy classes inside GL3FQ, SL3FQ and so on, what we were doing were looking at possible tori inside GLN and then seeing elements to be coming from those tori, right? So those are the things that we were doing. So this is about maximal tori in G sigma, and now suppose we go to semi-simple classes. So our Jordan decomposition tells you that it is enough to look at semi-simple classes and unipotent classes, provided you are getting some results on semi-simple classes in a general class of groups. So maybe there is some kind of a panda principle like Boris Kuniavsky has talked about, that also comes into play here. The statement that to which the panda principle applies is the statement that once you know all semi-simple conjugacy classes in all reductive groups, and if you know all unipotent classes in all reductive groups, then you can understand all conjugacy classes in all reductive groups. That's the statement, and the proof that panda principle applies will be by Jordan decomposition. So we will now concentrate for the remaining maybe 10-15 minutes of our lecture on semi-simple classes alone. So once again, a matrix or an element in your group is semi-simple if it is diagonalizable above, which means that when you take this faithful representation, under the faithful representation, the element will act by fixing some one-dimensional sub-representations of that particular representation. So that's how it will act by eigenvalues on those one-dimensional sub-representations. That's what one means to talk about a semi-simple element. And we made some noise about maximal tori, and indeed there is some very nice connection with these. So first of all, whenever we have a semi-simple element, it is contained in a maximal torus. Every semi-simple element of capital G is contained in some maximal torus in capital G, and all of them are conjugate. So whenever you are looking at semi-simple classes, it is enough to fix one maximal torus and see how many of conjugacy classes are there within G of the elements in this torus T. Okay, so you are looking at fixing some maximal torus. So for instance, you were looking at SLN, let's say, and then you look at the diagonal matrices inside SLN of K bar, and you are asking how many conjugacy classes of these diagonal entries can be. So of course, a diagonal matrix can be conjugate to a non-diagonal matrix. Once you change your basis, it can happen that something which is diagonal may not remain diagonal. But when are two diagonal matrices conjugate to each other? That's a question that one can ask. So if you have, when you have the while group action, so GLN while group is simply the permutation group, which will permute the diagonal entries. So by permuting the diagonal entries, if you are going to get from one diagonal matrix to the other diagonal matrix, by the while group action, you get the another element which is also diagonal. Then these two are conjugate by the corresponding permutation matrices, because W is acting by conjugation through NT. Okay, so when these two elements are W equivalent, then they are also NT equivalent. But the converse also holds. That means whenever you have two diagonal matrices which are conjugate in GLN, then their eigenvalues simply have to be permutations of each other. Of course, whenever two matrices are conjugate, their eigenvalues will have to be the same. So you may be writing them with some different permutations, different order. That's all that you have. But in general, if you were to look at a reductive group, you will need to use the Bruha decomposition to get this result. That whenever you have two elements, suppose you have one element and you conjugate it by some element in the group, then the element in the group will have some form given by the Bruha decomposition. People who may have come late, for them I may just tell you that whenever you choose a system of representatives for the while group inside your normalizer, then the same set also happens to be a set of representatives for the double cosets of Borel inside the group G. Okay, so you can write this conjugating element as B1 n B2. Okay, you are conjugating some torus element by B1 n B2 and you are getting another torus element. Then there are some standard modifications by which you can write this B2 as torus element times the unipotent element, and since the torus will commute, any two elements in the maximal torus commute with each other, you can ignore the torus element. So it is simply U1 n U2 conjugating a diagonal matrix to another, conjugating a maximal torus element to another element in the same maximal torus. And then the uniqueness will tell you that you can ignore these U's and it's only that n which plays this role. If you don't have that n does it, if the U's are non-trivial, then there is a small modification that you can do. So using Bruha decomposition, this is one very fantastic application of the Bruha decomposition, which tells you that whenever you take a reductive group, take two elements in a maximal torus. If they are conjugate inside the group G, then they must be equivalent under the action of the while group. And which is same thing as saying that, for instance, for GLN, you have that the eigenvalues are simply permuted. Okay. So the semi-simple conjugacy classes, once again, every element which is semi-simple has to be in a maximal torus. And by conjugating this maximal torus, you can bring it to your favorite maximal torus. So up to conjugacy, every semi-simple element has a representative in your favorite maximal torus. And which two of them are conjugate, that is understood simply by looking at the while group action. So theoretically, all semi-simple conjugacy classes are now understood. Although, you know, doing tutorial problems might still be small problem, it might be slightly non-trivial, but we will see that there are easier problems this time, something which you can do simply by hands. So the theory is very nice as far as semi-simple conjugacy classes are concerned. Okay, they are simply the while group orbits on the maximal torus T. Okay. Further, there is this very interesting result. I just cannot help but present it here. That if you have two semi-simple elements in your group G, we are assuming that our group is reductive. So if you have two semi-simple elements, then they are conjugate to each other if and only if for every character of the group, the values are the same, if and only if under every representation, the images are conjugate. So these all statements are equivalent. And in fact, if your group happens to be what is called a simply connected group, then these last statement and even the second statement, the third and second statement can be strengthened to be looking at only what is called the fundamental representation or the fundamental character. Okay. So semi-simplicity has some very nice connection for semi-simple elements. The conjugacy has some very nice connection with the representations of the group G. And this is the statement, this is the question which is asked in the paper. You know, so I don't know whether this is now known, that whenever you take G and H to be not semi-simple, does this result hold? So by that we mean that if you are looking at some group G and you have two elements G and H, if you have that under all representations, the images are conjugate, do we have that the elements G and H are conjugate? I do not know the status of this. Maybe, you know, some others may make a comment on this towards the end of this session. So after this question, we come to this very, very interesting statement, and this is what I had meant when I said that the conjugacy, the centralizers of semi-simple elements are reasonably well understood. That whenever, remember that we are continuing with our assumptions that our G is reductive or semi-simple and so on. If you take a semi-simple element, then the centralizer of that semi-simple element is a reductive algebraic group. It is already one of the nicest algebraic groups. So I told you that a reductive algebraic group will be an almost direct product of some very nice groups. It could be either a central torus or some simple algebraic group, something like SLN or SO2N, SO2N plus 1, SP2N, or there are these 5 exotic groups called exceptional groups. It has to be an almost direct product of these. So whenever you take a semi-simple element, its centralizer is a reductive algebraic group, and meaning the results that we have proved earlier will help you getting this structure of the reductive group. We have introduced the notions of characters, roots, and so on. So actually you can write down this centralizer precisely in terms of the roots, the while group elements, and so on. It may not always be connected, but quite often it is connected. And there is this one more result, which is that if your group is simply connected, so maybe since the notion of simply connectedness has come twice, let me try to tell you what it means. So a group G is a reductive group G is said to be simply connected if there is no finite cover of that. So what is a cover of a group? A cover is something which is obtained by, so cover is another algebraic group such that your algebraic group is obtained by going modulo a central subgroup. Okay. So if, for instance, if you are looking at PSLN, which is SLN modulo the scalars inside SLN, then SLN is a cover of PSLN because PSLN is obtained by going modulo the central subgroup inside SLN. You might take some of the in-between groups also. So you may not go modulo the full center of SLN, but you may go modulo a subgroup of that center. Okay, then you are going to get some in-between subgroups, and they are all covers of your PSLN. So therefore, your PSLN is not a simply connected group because it has non-trivial covers. But SLN is known to be a group which has no such finite covers, and therefore it is a simply connected group. Once you look at the roots, then again, there is a way to understand what one means by a group being simply connected. But since I have not explained all those terms, I will not get into it. But if your group has this another property that it is simply connected, and you have a torus T, which is fixed under the Frobenius endomorphism, then the statement which we had over algebraic closure, that the conjugacy classes which are of semi-simple elements are in bijection with T by W, that holds even in G sigma. That means that the semi-simple classes in this finite group is precisely the set of the classes you had above, and you take the fixed points. So whenever you have some set and you are putting a sigma below that, a subscript, that means you are taking all those points which are fixed by sigma. So the semi-simple conjugacy classes in G sigma, they are precisely, remember these are semi-simple below. We are not talking about semi-simple above and then you are looking at the conjugacy classes. No. We are saying that we have G sigma, we are looking at elements which are semi-simple in that finite group, and then we are looking at the conjugacy classes. Those are precisely T by sigma and T by while group, and then we are taking the sigma fixed elements. So these are very nice results, and I am almost close to the end of my time, and I also have this very last slide, that if you were looking at SLN, the semi-simple classes, so again maybe I should have said diagonal matrices really, because I am talking about the diagonal matrices here. So when you are looking at the semi-simple classes inside SLN, over algebraic closure, they will correspond to various possible characteristic polynomials. Because we know that the characteristic polynomials, their coefficients are given by some certain characters of the elements. And we know that for semi-simple elements, two elements are conjugate if and only if the corresponding character values are the same. So whenever two elements are conjugate, their characteristic polynomials are conjugate. And we also have the other way, that whenever the characteristic polynomials are conjugate, the matrices being semi-simple are conjugate. And just if you were to look at SLNFQ and if you were to look at the diagonal conjugacy classes, that number can be written down explicitly. And 1 minute, I am confused now about this last statement, whether it is only for semi-simple class or diagonal classes. The number being q power n minus 1. Can somebody clarify this statement? That when we are looking at SLNFQ and we are looking at the elements which are semi-simple, are we looking at all semi-simple conjugacy classes, or are we looking at only diagonal matrices which are semi-simple, which are in SLNFQ?
I think all semi-simple.
All semi-simple. Okay. Yeah. Thank you. So in general, so thanks Anupam. In general, indeed, now it comes back to me. So the result is that whenever you are looking at a semi-simple algebraic group G, and you have the dimension of the maximal torus, call that number to be R, then the number of semi-simple conjugacy classes in G sigma or GFQ is Q power R. So indeed, we are looking at all semi-simple conjugacy classes here. And so these are some very interesting results. In the next lecture, I will talk something about unipotent conjugacy classes, and then we will use the Jordan decomposition and study the general conjugacy classes. So that's all for now, and see you in the next lecture.
Thank you, Shripad. If there are any questions, we can wait for a minute.
So if no one is asking a question, I would like to go back to that particular slide and ask whether anybody knows about this status. I will try to look at that and come back in the next lecture.